Graph Theory Class 4 Video 1. In this video we're going to talk about Eulerian graphs. In particular we're going to talk about undirected Eulerian graphs. So if you recall from the previous video, an Eulerian graph is a graph which has an Eulerian circuit. And an Eulerian circuit is a circuit that hits every edge exactly once. Recall we also spoke about Eulerian trails, and an Eulerian trail is a trail that uses every edge exactly once. So a natural question to ask yourself is, which graphs have Eulerian circuits and which graphs have Eulerian trails? Okay, because not every graph has an Eulerian circuit or an Eulerian trail. It's just the way it is. Sometimes there are graphs that just don't have them. For example, if I draw this graph here, okay, then it's pretty clear to see that there is no Eulerian trail, and thus there is no Eulerian circuit. I mean, if you just think about it, if you want to hit every edge, you're going to have to repeat one edge to do that. At least one edge. You're going to have to repeat at least one edge to do that. This graph is non-Eulerian, has no Eulerian trail and no Eulerian circuit. So a natural question is, which graphs are and which graphs aren't? Well, fortunately, there's a really powerful theorem which tells you which graphs are Eulerian. And it's a very important theorem, okay? It gets 2 stars, so you should really pay attention to this theorem. So it says, an undirected graph has an Eulerian circuit if and only if these 2 conditions are satisfied. So the first condition, it's like a technicality condition. The first condition says every edge belongs to the same connected component. And what this is taking into account is, if I draw like a stupid graph, like this, okay? So this isn't 2 separate graphs, I'm calling this one graph, even though it's in 2 separate parts. It's not connected, I'm calling it one graph, okay? Well, obviously it's not Eulerian, because it's impossible to get from this edge to this edge, okay? So the first condition over here, this first condition, it's just saying you're not allowed stuff like this. So it gets rid of the really dumb examples. And the second condition says every vertex has even degree. Okay? And this is the important thing to remember. To have an Eulerian circuit, every vertex has to have even degree. And there's a second part of this theorem which tells you about Eulerian trails. So if you recall, a trail, you don't need to begin and end at the same spot. You can begin and end at a different spot. Whereas a circuit, you need to begin and end at the same spot. So it's harder to be a circuit than it is to be a trail. So an undirected graph has an Eulerian trail if every edge belongs to the same connected component. So that's the same condition as the previous one. But now condition 2 says at most 2 vertices have odd degree. Okay? Whereas in the first case, we said every vertex has to have even degree, so no vertex has odd degree. If you just want an Eulerian trail, you're allowed to have 2 vertices which have odd degree. Okay? And this is a very important theorem. And if you take a moment to appreciate it, it's a super powerful theorem, because it lets you calculate whether there exists an Eulerian circuit or a trail by just considering the degrees. All you do is you consider what are the degrees of the vertices. Okay? If all the degrees are even, this theorem tells you it has an Eulerian circuit, which is a very strong conclusion, considering some graphs can be very, very confusing. They can be super complex, and trying to find an Eulerian trail by hand might be difficult. But this theorem tells you straight away whether one exists or not. So let's move on to an example. This example right here. So the question is just, does the following graph have an Eulerian trail or an Eulerian circuit? Or maybe neither. Sometimes it has neither, and that's okay. Okay? So what you do is you just work out the degree of all the vertices. So this vertex here has degree 3, 2, 2, 1, 2, 3, 4, 5, 3, 2, 3. And now think about which ones of these are odd. That's 1, 2, 3, 4. It has 4 odd degree vertices. Okay? So by the above theorem, there is no Eulerian trail and there is no Eulerian circuit. Okay? That's it. It has 4 odd degree vertices, so the theorem tells us there is no Eulerian trail and there's no Eulerian circuit. Okay? But notice, this isn't immediately obvious if you just look at the picture. Like, you might be able to waste a significant amount of time trying to find an Eulerian trail. Like, you could spend a while trying to find a way of doing this, but it's actually impossible. Okay? And this is all because of the theorem. So let's do another example. This one's even more confusing. Okay? Same question. Does the following graph have an Eulerian trail or an Eulerian circuit? So let's just calculate the degrees. 2, 4, 4, 2, 3, 3, 2, 1, 2, 3, 4, 5, 6, 2, 6. So now, what are the odd numbers? I see there's a 3 and a 3. Okay? So there are 2 odd numbers, which means that that there is an Eulerian trail, but not an Eulerian circuit. So there exists an Eulerian trail, but no Eulerian circuit. Okay. One important thing to note about this theorem is it doesn't actually tell you how to find anything. It just tells you that it exists. So I know that there is an Eulerian trail for this graph, but the theorem doesn't actually help me in finding it. I have to find it by myself. It's just an existential theorem. It tells you, does it exist or does it not exist? Okay? One thing that you should note is a trail, an Eulerian trail, if there are 2 odd degree vertices, it always begins at one and ends at the other one. Okay? So I don't know exactly what the trail is, but I know that it must start at one of the odd degree vertices and end at the other odd degree vertice. Okay? So this is Eulerian trails and circuits for undirected graphs. That's the end of this video.